Hello everyone. In this video I am going to show you how to find deflection using method of double integration, and this is the example 3. So you can see our problem here. This is our beam. So you can see at A there is a pin support and at B there is a roller support, and at C there is a point load of P. So you can see I marked deflection here. So all the dimensions are given in this figure. So they ask the beam in figure is subjected to a load P at its end. Determine the displacement at C. EI is constant. So our first task is to find in support reactions. At A we have a pin support, therefore I mark two force components which are horizontal force component and vertical force component. At B there is a roller support, therefore I marked one vertical force component. First I will consider sum of all the horizontal forces. So if I consider horizontal forces, there is only one horizontal force which is AX. Therefore, AX is equals to 0. Next, I am going to take moment about point A to the counterclockwise direction. If I take moments, I will have By times 2A minus P times 3A. 3A is the this overall length. 2A plus A, it is 3A. So if I simplify this, I will have By equals 3P over 2. Next I will consider sum of all the vertical forces. If I consider vertical forces, I will have Ay plus By minus P equals 0. So I can substitute this By value for this By. Then I will have Ay plus 3P over 2 minus P equals 0. When I simplify this, I can get Ay equals minus P over 2. So this minus sign means this Ay force is acted not upward, it's downward force. So here you can see complete free body diagram. So I marked support reactions here at A and at B. So next I am going to cut this beam. So first I cut this beam through this point. Then I will consider this part alone. So this is the small part of beam, and this is shear force, and this is bending moment, and this is the support reaction at A, and I will mark this length as x1. Next I will consider this x2 part, so therefore I will cut this beam through this point. Then I will consider this part alone, and this is the A, and this is B, and this is the cut part, and this is the moment. So if I consider this x1 part, it's only valid for A to B. Equation I will obtain valid for A to B, and equation I will obtain from this part, this x2 part, is valid for B to C. So here is the common deflection shapes of different conditions. Anyway, we will have pin support and roller support. So at pin support deflection is 0, but there is a slope. Roller support also deflections are 0, but there is a slope. So next I will consider this small part alone. So you can see here a small part of the beam, and this is the support reaction at A, and this is the distance, it's x1, and this is shear force, and this is bending moment, it's marked as m1. So here's the range. These equations I will get from this diagram is valid for this range. It is 0 to 2a. So next I am going to find m1, it's the bending moment. For that I will take moment about point P, about counterclockwise direction. So if I take moments, I will have m1 equals minus px1 over 2. This is the equation for method of double integration. Next I will solve this equation for bending moment. So I will have this equation. Next I will substitute this m1 value for this capital N. So I will have this equation, and I will label this equation as equation 1. Next I will consider second part, which is x2 part, and you can see at A there is a support reaction, and this is point B. You can see support reaction of 3p over 2, it's support B support reaction, and this is the cutting part, and length is marked as x2, and you can see V2 is the shear force, M2 is the bending moment of this part. So here you can see range, it's 2a to 3a. Equation I obtained from this part of beam is valid for this range, it's 2a to 3a. So now I am going to take moment about point Q to the counterclockwise direction. If I take moments, I will have M2 equals Px2 minus 3Pa. Next I will again write equation for method of double integration. Next I will solve this equation for capital M, which is bending moment. Next I will substitute this M2 value for this capital M. So then I will have this relationship, so I will mark this equation as equation 4. So you can see equation 1 here. Next I integrated this equation 1, so I will have equation 2. This is the integration of this equation 1. Next again I will integrate this equation 2, then I will have this equation 3. So you can see equation 4 here, I showed you before. This is the equation 4. So I integrate this equation as well, so I will get this equation. This equation is labeled as equation 5. Then again I will integrate equation 5. Next I will have equation 6. So this is the integration of this equation 5. So you can see there are constants here, C1, C2, C3 and C4. Those are for indefinite integration. So we did indefinite integration, therefore we had to put a constant. So those constants you can see in this equation. So we have 4 unknowns, which are C1, C2, C3 and C4. Next I am going to find those constants. So for that I have to use boundary conditions. So let's see what are the boundary conditions we have. So this is our diagram. So at A we know deflection is 0. I can say when x1 is equal to 0, v1 is equal to 0, which means deflection is 0. That is the first boundary condition. And also I can write boundary condition and also I can write boundary condition for point B, which is roller support. So roller support also deflection is 0. So I can say using this x1 coordinate, when x1 is equals to 2a, v1 is equals to 0. That is for this x1 coordinates. Using this x2 coordinates, I can say this point B, when x2 equals 2a, v2 equals 0. So here also I can write relationship for this point B using its deflection. So these are the 3 boundary conditions. So you can see there are 4 unknowns, so therefore we have to build another relationship. So first we will do what we can. So first I will use these 2 boundary conditions. So I will substitute v1 equals 0 at x1 equals 0 to the equation 3. So when I substitute it, I will have c2 equals 0. Then I will substitute v1 equals 0 at x1 equals 2a. So from equation 3 I can substitute those values. Now I know value of c2, I found it before, it equals to 0. So I can substitute it, then I can get the answer for c1. Okay, now I got 2 answers from 2 boundary conditions. So if I look at this diagram, so if I look at this boundary condition, so I can use this equation 6, but if I substitute these values, I will have 2 unknowns because I don't know c3 and c4. Therefore no point of substituting these boundary conditions for this equation 6. Therefore Now I'm going to build another relationship. For that, I can draw a horizontal line here, and I can mark this angle as theta 1. So that is the slope. So here also an angle. So I will mark that angle as theta 2. This is the roller support. So these are the slopes of this support. So using geometry, I can say here theta 1 is equals to theta 2. We know slope equals to theta, theta equals dv over dx. So using this relationship, I can write d1 over dx1 equals dv2 over dx2. So using this theory, I can build another equation. I will substitute x1 equals 2a because I will consider this support, and when I consider x1 coordinate, I will have to substitute x1 equals 2a to reach this support. So I will substitute x1 equals 2a and c1 equals pa squared over 3, which is we found it before, to the equation 2. If you closely look at these 6 equations, you will find here dv over dx, which is slope. Here also you will find dv over dx, which is slope. So I can use this equation 2 and equation 5 to build another relationship. I will substitute x1 equals 2 and c1 equals pa squared over 3 to equation 2. So this is equation 2. So if I substitute these values, I will have this equation. So it's equals to ei theta 1, and I will label this equation as equation A. Then I will substitute x2 equals 2a. So if I consider x2 coordinates, here also I have to substitute x2 equals 2a to the reach this B support. So therefore I will substitute x2 equals 2a to the equation 5. So this is the equation 5, and if I substitute this, I will have this equation. I can equal it to ei theta 2, and I will label it as B. Since theta 1 equals theta 2, I can say capital A equals to capital B equation. So I will equal these two equations, and if I equal this, you will see there is only unknown, which is C3. So I can solve this equation and get the answer for C3, and finally C3 is equals to 10 over 3 p a to the power 2. So now I know C3 value. Next I can use my final boundary conditions. Because now I know C3, I can apply this boundary condition for equation 6. So I will substitute V2 equals 0, x2 equals 2a, and C3 equals 10 times pa to the power 2 over 3 to equation 6. So this is the equation 6. So I can substitute these values, and only unknown here is C4. So I can solve this equation and get the answer for C4. C4 equals minus 2p a to the power 3. So now I know all 4 constants. So finally I can find deflection of point C. In order to find displacement of at C, substitute x2 equals 3a to equation 6. So this is the equation 6. I will substitute x2 equals 3a as these values. Here I know all the constants, so therefore I can substitute C3 value for this C3 and also C4 values for this C4. So if I simplify this, I can get Vc equals minus Pa to the power 3 over Ei. So if I substitute these values, this V2 becomes Vc, because the deflection which we get from this equation is deflection of point C. When x2 equals 3a, this reach this point. So this is the point C, and deflection we will get from that equation is deflection of point C, which is Vc. So this is our final answer, deflection of point C.